If you've ever taken a single variable introductory calculus course in your lifetime, you're probably familiar with the world-renowned mathematical operation, the integral. Integration is used in many mathematical and scientific fields, but we're not going to dive into that. Instead, I want to introduce or maybe refresh you on something crazy. Normally, if I were to take the integral of, say, a parabola, the quadratic equation x squared, the antiderivative would be x cubed over 3 plus c, right? And if it were definite, say from 0 to 2, I would get 8/3. But what if I had a more confusing looking function? Say I had the square root of 1 minus x to the power 4. Now what if I took the integral of that? Except it's not quite so easy to integrate as x squared was. The average calculus student would lose their mind trying to solve this. So how do we solve it? Well, before we get to that, we have to discuss some history first. In the late 17th century, the period of the scientific revolution was at a time of major advancements in astronomy, physics, and most importantly, to us at least, innovation in mathematics. Numerical calculation, symbolic algebra, analytical geometry, and other fields were greatly advanced. But then came the invention of differential and integral calculus. Historian Carl Boyer referred to calculus as the most effective instrument for scientific investigation that mathematics has ever produced. Calculus itself was born from two great minds, German Gottfried Wilhelm Leibniz and Englishman Isaac Newton. There was a long and difficult dispute over who really invented calculus, but at the end of the day, it seems like the two discovered it independently of each other. Calculus, also known as the calculus, came from the techniques of solving two specific kinds of problems: figuring out areas and volumes easily, and calculating tangents to curves. Before calculus, mathematician Archimedes had used classical geometry with a technique known as the method of exhaustion, where they would establish the results of areas and volumes manually, using logical methods to prove areas of figures using the rule that something can be made smaller by having it some number of times, which was used to prove that the area of a circle was proportional to its radius squared, also known today as a equals pi r squared. After this pre-calculus period, beginning in the 1820s, a variety of mathematicians used the idea of a limit to establish calculus on an arithmetic basis, including Bayer and Cauchy. Their algebraic viewpoint that other mathematicians such as Leonhard Euler and Joseph Louis Lagrange held. But even as calculus was growing and becoming more rigorous and refined, mathematicians were already starting to run into confusing integrals that couldn't be solved using traditional methods. Getting back to what I introduced to you earlier, that function, the square root of 1 minus x to the power 4, its story originates with a supposedly simple problem: finding the arc length of an ellipse. Way back in 1655, mathematician John Wallis had already tried to figure this out, where both he and Newton had established infinite series expansions for it. However, no one could find a simple and straightforward closed formula, and that greatly frustrated the two. Despite the great power of calculus being at their side, a simple geometry problem fought back and showed them things were not as simple as they originally thought. But then in the 1690s, Jacob Bernoulli encountered similar integrals while studying mechanical problems on his own. In 1694, he was observing the shape an elastic rod takes when compressed at the ends, and he discovered a figure 8-shaped curve called the lemniscate. He started to calculate the arc length of the lemniscate, and he came up with the integral from 0 to some value x for dt over the square root of 1 minus t to the power 4. And if you'll notice, this equation looks very similar to the one from before. And just like in our example, it couldn't be solved with known functions like polynomials, trigonometric functions like sine or cosine, exponentials, or even logarithms. These known functions are known as elementary functions, by the way. These sorts of integrals were mysterious and confusing, and seemed to be in their own special category, which we now call non-elementary integrals. For decades afterwards, these sorts of integrals would pop up and remain a mystery. But then a breakthrough came with Italian mathematician Giulio Carlo di Fagnano in 1718, where he discovered the addition and multiplication formulas for arcs of the lemniscate. So even though there was no simple formula, he figured out relationships between different values of the integral, and had his work republished in 1750, sent to Berlin Academy for Leonhard Euler to review. When he saw Fagnano's work, he immediately noticed something revolutionary had been at work. He quickly presented his own paper with even more derivations and had developed a general addition theorem for these integrals within a few years. These strange integrals that came from ellipses, lemniscates, and other curves became known as elliptic integrals, including that example from earlier, the square root of 1 minus x to the power 4. But what even is an addition theorem? Considering this equation that involves a hopefully familiar integral, if we set y equals sine u and z equals sine of v, we get something equivalent. Also note that we define t as following. But let's put it in plain English. An addition theorem is simply just a theorem for a function f that expresses f of u plus v in terms of f of u and f of v. Or to connect to that previous example, a function f has an addition theorem if there exists a two-variable function t where f of u plus v equals t of f of u f of v. Some examples of functions that have addition theorems are e to the x, sine of x, tan of x, and more. The function t for each of these respectively is the following. Now back to what Euler had to discover, he specifically expanded on Fagnano's work by finding the following. For this differential equation, where c is an arbitrary constant. If you do some rearranging, you get the following, where the second integral on the left is a convenient expression for the constant of integration. Then we can write it in another form, and we get t uv once again, which is a function that generalizes what Fagnano discovered, which was basically this, where r equals t of u, a distance from the origin, the lemniscatic arc length for that point being twice that of the point u from the origin. Crazy stuff. But putting all of this discovery aside, we technically haven't answered the original question of what the integral of square root of 1 minus x to the power of 4 even is still. The closest answer I could find was according to user Math Machine on the Mathematics Stack Exchange almost 10 years ago, and here it is. This crazy looking answer does need some clarification, in particular to students unfamiliar with more advanced calculus. Firstly, the e function represents the incomplete elliptic integral of the second kind, which is just a special type of elliptic integral that takes two parameters, phi, or the amplitude, which is how far along we're integrating the function in this case, and the elliptic modulus squared m. It's squared as m equals k squared, which equals sine squared of alpha, where k is the elliptic modulus and alpha is the modular angle, as shown. Additionally, those vertical bars essentially just represent an evaluation, which means in the context of e arc sine with -1 just means the elliptic integral e evaluated at angle arc sine x with parameter m equals -1. So basically just means evaluated at with this given parameter. Now things get deeper than this, but I think you get the idea. There's a lot that goes into these integrals, but there are other integrals that are non-elementary, which are non-elliptic. For example, there's the logarithmic integral 1 over ln x, the Gaussian integral e to the -x squared, Frenet integral sine of x squared and cosine of x squared, the sine integral sine of x over x, the exponential integral e to the -x over x, e to the x, ln of ln x, and a special form of the gamma function where we have x to the c minus 1 e to the -x, where if c is any positive integer, it would be elementary, but if we had c equals 1/2, then we would have the error function, and c equals 0 would be written in terms of the exponential integral. Some of these I could dive into in greater detail, but I think that's it for today. The main point I'm trying to get across is that calculus can get really interesting and strange, and not as simple as the noble x squared. I could have dived into the Rich theorem, which is able to calculate antiderivatives using a computer, or how central limit theorem, an important topic in probability theory, involves the Gaussian integral I discussed, and how that ties into how it works. But I think I'll leave that stuff for you guys to explore, and I'll be leaving my sources down below. Thanks for watching everyone, and I hope this video helped you learn something new today.